Hello everyone, I'm going to present our work titled Toward Mobile 3D Vision. My name is Huanle Zhang from the University of California, Davis. The co-authors are Ham from the AT&T Labs and my advisor Prasant Mohapatra. In the past few years, the computer vision community has developed many novel technologies of 3D vision. In this position paper, we explore the opportunities brought by these innovations for enabling real-time 3D vision on mobile devices. The key differences between 3D vision and 2D vision mainly stem from the input data format, that is, point clouds or 3D mesh versus 2D images. Hence, the key challenge of 3D vision is that it could be more computation-intensive and memory-hungry than 2D vision due to the additional dimension of input data. In this position paper, we present a research agenda on offering systems of support for real-time mobile 3D vision, focusing on improving its computation efficiency and memory utilization. 3D vision has the depth information which is crucial for many applications. First, an autonomous car not only needs to detect objects such as other cars and pedestrians, but also determines the distance between the objects and itself. Second, moving robots and flying drones need to understand their surrounding 3D environments to plan routes intelligently and avoid colliding with nearby objects. Third, co-present avatars for those who are at different locations can benefit from 3D vision for better understanding of the surrounding environment. We use object detection and scene segmentation as examples for 3D vision because they are key components for 3D vision systems and applications. In object detection, each 3D object of interest is localized, whereas in scene segmentation, each point of the input point cloud is classified with a label. From the application perspective, scene segmentation can be used for object detection, which in turn can be used for object classification, but not vice versa. There are two common representations for modeling 3D objects, that is, 3D mesh and point cloud. DL models for processing 3D meshes are currently constrained on manifold meshes such as organic objects, and it is not obvious how to extend such models to a scene that includes multiple non-isometric objects such as furniture. By comparison, a point cloud is an unordered set of points. Each point has its coordinates x, y, z, and a property p. Point cloud is a simple and unified data structure that avoids the combination, irregularity, and complexities of 3D mesh, and thus it is easier for DL models to learn from. For different applications, P has different formats, as the figures on the right side illustrate. Different methods of feature extraction result in different degrees of data dimensionality, which in turn determines the model complexity. We categorize the mainstream methods of 3D feature extraction for point clouds and investigate an example DL model for each category. Specifically, we use the complex YOLO for the category of converting to 2D feature vectors, VoxNet for a feature vector for each grid cell, point pillar for a feature vector for each pillar, and SparseConnect for a feature vector for each point. This table tabulates details of the selected DLN models. Complex YOLO, VoxNet, and point pillars are 3D object detection models. SparseConnect is a 3D scene segmentation model. The table also shows the accuracy reported by these papers. As expected, the complex YOLO has the lowest average precision in detecting cars as it relies on 2D features. SparseConnect achieves a high intersection over union and is one of the most accurate models for the SkyNet segmentation database. To understand the performance of complex YOLO, VoxNets, point pillars, and sparse nets, we implement them and measure their computation and memory overhead on a server and two smartphone models. We use TensorFlow Lite for complex YOLO, VoxNets, and point pillars, and PyTorch for sparse nets. For the implementation on the server, we use TensorFlow Lite on phones for the first three models as it provides optimized acceleration for executing the models on mobile devices. We lead as future work to implement the sparse CommNet on smartphones. Unless otherwise stated, we conduct experiments on CPUs. This table tabulates the execution time per point called and the memory consumption of these models on the server. We can see that different categories of models have dramatic performance differences. 90 times in speed and 190 times in memory overhead when comparing the heaviest model VoxNet and with the lightest model Compressio. In addition, we have the following observations for each model. Compressed YOLO is lightweight. However, the accuracy is low. VoxNet is extremely slow and requires tremendous memory because the model generates a large number of grid cells and features. Point pillars dramatically reduce the computation and memory overhead compared to VoxNet. Sparse CommNet is efficient. Even so, it takes a significantly large number of points as input and is designed for scene segmentation, which is more challenging than object detection. It requires only an average 1.8 seconds per point called. We compare the execution time of the model running on the Huawei Mate 20 phone versus on the server. This figure shows the execution time of complex YOLO for 100 runs. On average, Huawei Mate 20 takes 1.3 seconds per point called, which is about 4 times slower than the server. This figure shows the execution time of point pillars for 100 runs. The phone runs more than 300 times slower than the server. This is because the TensorFlow Lite does not support the variable length 1D convolutional layer, which is used by point pillars to generate the feature vectors of all the pillars. Instead, we trigger a function call to generate a feature vector for each non-empty pillar on the mobile device, which incurs a significant delay. We expect a similar performance comparison of point pillars on the phone versus the server as a complex YOLO if TensorFlow Lite supports the variable length 1D convolutional layer. An intuitive way to speed up the execution of a model is to run it on GPU. However, a practical challenge is that if some model operators are not supported by the GPU, TensorFlow Lite has to execute only a part of the model on GPU and the remaining on the CPU. In this case, due to high cost of synchronizing CPU and GPU, the model execution with GPU may even be slower when the model is run solely on the CPU. Take complex YOLO as an example. The execution time increases from 1.3 seconds for CPU alone to 2.3 seconds with GPU and CPU on Huawei Mate 20, and 2.6 seconds for CPU alone to 3.4 seconds with GPU CPU on Google Pixel 2. From the measurement results, we can see that it is challenging to support grid vision in real time on mobile devices. Now these models can execute faster than 1 point cloud per second. As a continuous vision system, it is typically preferred to be faster than a dozen Hz, and thus there is still a gap between the current and the desired speeds. Besides, these models require larger than 0.4 GB memory, which is demanding for smartphones since memory is shared by many applications. In summary, there are tremendous opportunities for reducing the computation and memory overhead of DNN models in order to enable real-time 3D vision on mobile devices. Our preliminary measurement results about demonstrated the challenges of mobile 3D vision. We identified 5 areas for potentially improving the efficiency of executing 3D vision in real time on mobile devices by presenting the challenges and possible solutions for point cloud-based object detection and scene segmentation. Specifically, we consider the dynamic input, offloading, model selection, locality in continuous vision, and hardware parallelism. The input size significantly affects the DNN model complexity because a more powerful DNN model is needed for fitting a large input. At the scale, train several 2D object detection models for different image resolutions and designs a neural network to predict the optimal downsampling factor for each input image. Based on the prediction, the input image is downsampled, and then the corresponding model for that image resolution is used. We find that instead of training several models for each point cloud size, we can use a single pre-trained model for point clouds of any size. The figures on the right side show the performance of a pre-trained model with regards to the accuracy and the computation overheads using different sizes of randomly simplified point cloud. The performance at 100% point cloud size represents the model performance without data simplification. We have the following observations. First, the model accuracy remains almost the same even when only about 60% points are used. Second, as we can see, the computation overhead is approximately linearly correlated with the point cloud size. Therefore, it is preferred to space point cloud as long as the accuracy does not significantly drop. However, it is still unknown how to predict the optimal downsampling factor for each point cloud, which is part of our ongoing work. A cloud server, either at central data center or at the network edge, is usually equipped with much more powerful hardware than mobile devices. Therefore, offloading computation-intensive tasks to the cloud can elevate the hardware constraints of mobile devices. However, offloading low data is not always practical because of the large size and privacy concerns. Furthermore, the standard of point cloud compression is still under active development, and there is no widely adopted hardware accelerator for point cloud compression. It remains an open problem on efficiently identify regions of interest for point clouds. Moreover, the processing of raw data on mobile devices may potentially increase the end-to-end latency. Hence, an interesting research direction is to investigate how to balance the trade-offs between accuracy, bandwidth, and the end-to-end latency for continuous mobile 3D vision. There are generic techniques to reduce the complexity of DNN models, including parameter quantization and network blurring. However, these standalone techniques do not consider the runtime resources of mobile devices. For example, a smartphone that has many background processes may prefer a fast model in order to reduce the end-to-end latency. A smartphone that has limited remaining battery may prefer an energy-efficient model. A possible solution is to automatically select a model from a pool that balances various resource accuracy trade-offs. As cameras output images of the same resolution, the model's computation and memory overhead can be determined in advance to facilitate the selection. By comparison, a 3D scanner generates point clouds with different number of points. Therefore, different point clouds result in different computation overheads for data processing and DLM model execution, which makes the prediction of the runtime resource overhead of point cloud-based 3D vision systems, and thus the model selection difficult. One approach to reducing the computational workload of continuous vision is to explore the temporal locality of consecutive images or frames. Instead of running object detection on each input, we can treat the video as a sequence. Object detection is only performed for two frames that are geometrically different, and catching is used for frames in between. In 2D object detection, an image is divided into several blocks, and then blocks in two consecutive frames are compared to for object tracking. A recent advance is to apply a neural network to predict the object locations in next frames, which can greatly improve the tracker accuracy. However, 2D tracking technologies may not be directly applied to point clouds because of the much larger search space of 3D domain. Recently, Frontnet 3D built a DL model for tracking scene flow in point clouds and shows promising results. However, the computation overhead of Frontnet 3D is too high to be applicable for mobile systems. Hence, designing a lightweight tracker for point clouds remains an unsolved open problem. Smartphones are equipped with many computation resources such as CPU, GPU, and DSP. It can greatly speed up model execution if all these resources can be used in parallel. However, different hardware have varied computation capabilities and memory size. The heterogeneity of this hardware makes the parallelism difficult, and it is crucial to consider the capabilities of different hardware resources when parallelism model execution. There are two straightforward methods of parallelism based model system. One, parallelism DLM models. We can partition a DLM model into three parts and run each part on CPU, GPU, and DSP. However, it is unclear how to optimize op- optimize the model's partition. The actual inter-hardware communication overhead should be taken into consideration and minimized. 2. Parallelism input data. MobiS partitions an image into small patches and runs these patches on multiple hardware in parallel. Each hardware runs a model tailored to its capability, and a scheduler is designed for determining which patch runs on which hardware based on the complexity of the patch. However, partitioning a point cloud is more challenging than partitioning an image. Conclusion: Our preliminary measurement study reveals that it is not only computation-intensive but also memory inefficient for mobile devices to execute existing DNN models for 3D vision directly. We present a research agenda for accelerating these DNN models and point out several possible solutions to better support continuous 3D vision on mobile devices by considering the unique characteristics of point clouds. That's all. Thanks for your listening.